authored by Asad, Jeewa, Anban, Pillay, and Edgar, Jembere. It's on learning to generalize in sparse reward navigation environments. You're welcome to start, Asad, whenever you're ready.
Sorry, I was on mute. Thanks, Komi, for the introduction. Everybody can see my slides?
Yes, we can, perfectly.
Okay, perfect. Let's go straight into it then. Okay, so as I was introduced, we're going to be focusing on generalization in sparse reward environments. So specifically, what does that entail? We're working in the domain of reinforcement learning, where an agent has to interact with an environment, the environment returns rewards, and the agent learns behavior by maximizing long-term rewards. So let's break down that problem further of generalization. Firstly, we know that in general, AI is good at doing very specific things, and there's a push towards making that happen. The next big phase in AI is changing that. But specifically in reinforcement learning, a lot of research indicates that when you make small changes to an environment, this leads to dramatic decreases in performance. For example, here's an image here of agents trained in a Mario environment in the day, and they struggle to work with the same algorithm when you tested them in levels where just the texture was changed of the night. And a major issue with this as well is that reinforcement learning agents traditionally are evaluated on the environments that they were trained upon, unlike machine learning. And there is also a push to change this as well. The second part of the problem is that of sparse reward environments. So I said that reinforcement learning is based on learning from rewards from the environment, but prevalent in the real world, and very often the case is that the environment does not return enough feedback for the agent to learn. So how do you learn when this reward signal is so weak? So this is a very active research area. There's a lot of research in this space, but these novel algorithms that are being produced very much focus on learning the specific tasks and not necessarily on generalization. So we chose to investigate the problem of generalization in these sparse reward environments, particularly focused within the domain of navigation. So let's set the scene on exactly how we did this. We created a set of handcrafted maze environments where the task of the agent is to navigate to distant targets in environments with different obstacle configurations. So we'll go into further detail in a few seconds on the specific environments, but basically the agent is able to observe its position, the position of the target, and its distance to the goal, and is equipped with rays that extend in 45-degree angles to be able to detect obstacles in front of it and adapt its movement as required, as is seen on the image over here. And this image also indicates the scale of the task on the right. The agent is able to move in 8 directions, up, down, left, right, diagonally, and it's rewarded +1 for finding the target and -1 over M, where M is the maximum number of episode steps on every episode. So this makes it a sparse reward environment because it only receives positive feedback upon completing the task. And in our paper, we go into details on how we verified that this is a sparse reward environment. So borrowing from machine learning in supervised learning and traditional approaches, and what was indicated in the literature for generalization in sparse reward environment, it's very apparent that there's a need to create a separate set of training environments and a separate set of testing environments. So that's exactly what we did. We subdivided the training environments into 2 categories. Number one, those with single obstacle, we call them single obstacle training environments, where there's only a single obstacle and that varies in a scale as well as orientation, as you can see in the image. And then more difficult training environments, which are mazes. And what we tried to do here was create a diverse yet representative set. So each environment, an environment aimed to represent a learnable characteristic. So if you see this in an unseen environment, something similar, you should be able to mimic the behavior that you learned in the training environment. For example, a dead end or multiple path the target. So if we see these features in training, as you do with machine supervised learning, then hopefully in unseen environments, if similar features are found, then you can succeed in those environments. And we divided these training environments into standard and difficult categories. The difficult categories are either more complex versions of the standard mazes. As you can see in the image, my laser doesn't seem to be working, but yeah, it has multiple obstacles that span more than half the entire width of the environment. The testing environments, we divided that into two categories because we wanted to test agents were trained only in the set of training environments and whether they were able to succeed in unseen environments. So there were two types of unseen environments. One, orientation environments, where we simply rotated the training mazes by 90 degrees as shown in the picture. But even though that sounds trivial, you can notice that the path to the goal changes significantly just by doing this. And the second set was completely unseen obstacle configurations to training. There may be similar features, but these particular obstacle configurations were completely unseen in training. So how did we go about looking to solve, or not solve, but improving generalization in these environments? So our work focuses on curriculum learning. So the task of learning the skill of finding targets in an arbitrary environment, it's a very difficult task. And it's not straightforward how you would go about learning that. So we aim to make the learning process more easier for the agent, and by using curriculum learning. And what that does is it imposes an order on the training, and it enables to learn a task. And instead of learning it directly, you learn it in stages. So we perform twofold difficulty adjustments. We started with small environments, and then we continuously increased the size as the agent learned sufficiently the task. And we also then first selected single obstacle environments. Once the agent had sufficiently learned that task over reaching a reward threshold over 5,000 consecutive episodes, that's when we then started sampling maze environments, which are more difficult than obstacle environments. And once it sufficiently learns this task, we then keep increasing the size until eventually you get to the most difficult version of the task, which is the original task that you want to learn. Two other features of how we were able to bypass the sparse rewards problems with this curriculum here, and I won't go into further detail, that's in the paper, but at the start of every episode, we randomly set the agent start point and the target start point. So naturally, there'll be times when the agent and the target are close together. So this acts as a means of bypassing the sparse reward problem. And also we randomly sample an environment from a category of environments. So we randomly, for example, sample an obstacle environment, and that now is a means of ensuring diversity in your training. So you aren't learning a single environment or very few environments. You want a policy that's seeing a lot in training so that it's not learning, memorizing specific paths to the goal. What did we compare this? So this curriculum was a manually designed curriculum which we present in the work, and we needed to evaluate it against other algorithms from the literature. And one means of learning in these environments that was seen very often was that of curiosity-driven exploration. So what does this do in terms of sparse rewards environments? When the environment is giving you 2 less rewards, this is an intrinsic reward that the agent creates itself. And what it does is it's a reward that encourages agents to find novel states. So this was one of the baseline algorithms that we compared our curriculum to. And also we wanted to see if there were any merits to combining the curiosity with the curriculum. So our final baseline was a hybrid approach. I won't go into the details on the experimental design and the hyperparameters. We used the proximal policy optimization as the policy gradient method behind each of these 3 algorithms for consistency. And yeah, we can details on these algorithms and hyperparameters are in the paper. But let's look into the most important thing, which is the actual results. So what we did here was we performed 5 independent runs on each algorithm: the curiosity, the curriculum, and the hybrid. We depict the mean curve, and we show the standard deviation. So what you can see from the graph on the left here is that the curriculum graph never drops low. So it's average rewards that it obtains in a single episode. An episode is basically once the agent finds a target or a maximum number of episode steps are reached, an episode terminates. So you can see, unlike the red curve, the blue curve never drops too low because of this difficulty controlling, and the task is never too difficult, so it's constantly getting reward feedback. And secondly, when the task drops slightly, that's when the difficulty is increased. It very quickly recovers, which means that there is a steady transfer of knowledge occurring throughout this curriculum. And then the graph on the left also indicates that the curriculum agent also converged faster than the curiosity approach. Now, this is the main thing that we wanted to focus on, was how do we assess the generalization of this curriculum? So what we did was we selected the best performing training run of each algorithm. we evaluate that agent on 1,000 episodes. We randomly sample from each of the testing categories at the start of each episode. And very importantly, there was no policy fine-tuning happening over here. We trained entirely on the training environment, and we wanted to see how much knowledge was transferred. So you can obviously improve results with fine-tuning, which is a very profitable avenue in literature, but that's not the focus of this work. So the first result here is, I said that the curriculum, what the curriculum was doing was that it was aiming to bypass the sparse reward problems by randomly selecting the start and the goal position at the start of every episode. So what we did, we needed to verify that it was actually able to learn in the sparse version of the task, where the start and the goal position was made as far as possible in the largest version of the environments. And we can see that all 8 algorithms were able to learn and succeed in these environments. This curve basically there's no time to go into details, but this curve basically shows the average reward across the 1,000 episodes. And when it's approaching 1, that means on almost every run, it found the target. So you can see that this acts as a verification that sufficient knowledge was learned so that we can analyze the performance further and the comparison is fair. So now we look into the different categories of testing environments, and we see that in the new environments, even though these are completely unseen characteristics to training, all algorithms were still succeeding. So there's nothing so interesting here except the success across the board. And then now, as you go into more difficult environments, you can see naturally that the average rewards drop. But this is when things start getting very interesting, is when you get into the difficult environment, is when the curriculum agent clearly starts taking the lead, for lack of a better explanation. But what's going on here is that the curriculum agent is able to, the average reward has dropped below 0, meaning that on most runs, it isn't finding the target. But this was expected somewhat because we created these difficult environments to test the boundaries of the algorithm. So the curriculum agent was actually able to find the target on 2 of the 5 environments, whereas, for example, the curiosity only succeeded on 1, and it was significantly longer, the time, the number of steps it took to find the environments. And the most promising result here is in the hardest, most difficult set of environments, where the curriculum agent was the only agent to be able to find the target in this difficult spiral maze, which is a famous environment in the literature. And what's encouraging is that it's a very difficult, it's a very specific set of movements that the agent has to take to actually make it to that target. Okay, so I'll just very quickly, we also looked further into what the curriculum was learning and analyzed the movement patterns of the agents. And there was some promising results that we were able to see that the agent sort of uses the walls around it to adapt its movement. So it's learning somewhat robust policies. And a major benefit of the curriculum as well is that it completely removed the need for reward shaping, because traditionally with sparse reward environments, if the environment isn't giving you enough rewards, you need to find a way of creating rewards for it. And that's very difficult when it comes to generalization. So through the curriculum, we were able to bypass the need for reward shaping as well. And importantly, this information may not be available to you. That information that you need in order to augment the reward signal, it may not be available to you in the real world. So it isn't, it's another benefit that you don't need that in this setting. So just to conclude, we presented a manually designed curriculum that enabled better knowledge transfer to unseen training, testing environments when compared to curiosity and hybrid approaches. However, which we didn't have time to go into the limitations of the algorithm too much in this presentation, but in the trajectory analysis where we looked deeper, we found issues where agents were tending to get stuck in local optima and they tended to repeat movements. So this leads us to our future work and how we'd like to bridge that gap further. One way would be to increase the memories of the agents by giving them a longer sequence of observations. And we'd also like to perform larger scale analysis. Instead of manually designing these environments, a very promising avenue in the literature is that of procedural generation. And that will allow us to form a more larger scale analysis and see if the same principles hold. Yeah, so that's just a very brief overview of our work. I'm happy to take questions and also just chat offline about these things. But thanks for your time and thanks for the opportunity.